Hello, and welcome back to Advent of Code 2005 Day 8, a series where I'm going to continue playing Advent of Code, solving Advent of Code problems until I no longer am having fun doing Advent of Code problems, and I'm still here, so I'm still having fun. We're going to knock this out, and then I think we're going to play Pikmin 2 today, because that was what Patreon picked for our game this month. Day 8, Playground. Equipped with a new understanding of teleporter maintenance, you confidently step onto the repaired teleporter pad. You rematerialize on an unfamiliar teleporter pad and find yourself in a vast underground space which contains a giant playground. Across the playground, a group of elves are working on setting up an ambitious Christmas decoration project.
Can you use this money?
Every Advent I wake up and open Palm Slam Visual Studio Code right open. It's whole bunch of garbage Python code, and right then and there I start writing the code, all the while complaining about the global interpreter lock. I do every thread wrong.
Thank you so much, Carrie. I appreciate that. Across the playground, a group of elves are working on setting up an ambitious Christmas decoration project. Through careful rigging, they have suspended a large number of small electrical junction boxes. Their plan is to connect the junction boxes with long strings of light. Most of the junction boxes don't provide electricity. However, when two junction boxes are connected by a string of lights, electricity can pass between those two junction boxes. The elves are trying to figure out which junction boxes to connect so an electricity can reach every junction box. They even have a list of all the junction box positions in 3D space. This list describes the position of 20 junction boxes, one per line. Each position is given XYZ coordinates, so the first junction box in the list is at X162, To save on string lights, the elves would like to focus on connecting pairs of junction boxes that are as close together as possible, according to straight line distance. In this example, the two junction boxes are closest together, so yeah, Euclidean distance. By connecting these two junction boxes together, because electricity can flow between them, they become part of the same circuit. After connecting them, there is a single circuit which contains two junction boxes, and the remaining 18 junction boxes remain in their own individual circuits. Now the two junction boxes which are closest together but aren't already directly connected are blah 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 after connecting them. So we're just doing a min spanning tree on a implicit graph. Okay, let me make sure I'm reading this correctly. After connecting them, there is now a single circuit which contains 3 junction boxes and additional 17 circuits which contain 1 junction box each. After the next 2 junction boxes to connect are blah blah blah. The next 2 are these 2. They were already in the same circuit, nothing happened. This process continues for a while, and the elves are concerned that they don't have enough extension cables for all these circuits. They'd like to know how big the circuits will be. After making the 10 shortest connections, there are 11 circuits. 1 which contains 5, 1 which contains 4, and 2 which contain 2. So it does want me to join the ones in the same circuit? Okay. Sure. Why not? Really looked like they were going to have me make a min spanning tree, but it does not look like that's the problem, which is weird. So I'm just going to make a list of all pairs, sort it, and take the top ones, I guess. I don't know. Best I can figure. I'm probably organizing this poorly. Hey, Ash. Hey, why? I'm probably solving this in a really dumb way right now. No, but I don't actually care about the distance between them, because I don't want to take the square root. The square root's a costly operation, and I can just keep the value without square root, and it'll be cheaper. I don't want it to actually calculate distance. Okay, so I want to build an adjacency list, I think, is the answer. Oh, no. I'm not saying, like, it's not going to be fast enough. I'm saying, like, the hyper-optimization part of my brain is saying I can make it faster by not taking the square root. I really hate using default dict. I don't know why I hate that class so much, but I really do. There's a collections. So now I'm gonna make all pairs, so... Pairs dot push, no, append. Okay, so I sorted that, and now I want to basically take all the smallest connections and combine them. I'm like, my brain is going back and forth between like 4 different ways I can implement this, and I'm just not deciding what I want to do very well. I'm just going to implement DFS. I just don't care that much. I'm just going to implement DFS. For D box 1, box 2 in pairs up to just the first 1,000. Not visited. And I have connections. I have to think about this. Calling DFS visit, I mark it as true, then I look at all of its adjacent nodes, and if I've not visited box 2, I'll write it this way, it's fine. If I've not yet visited box 2, then I call DFS visit on box 2. Every time I initiate a new call, too low. Why would that not work? Every time I initiate a new call to DFS visit, I increment my connected component counter. Because I'm just counting number of connected components after all these connections, right? Oh, no, that's not the whole problem. That's counting the number of connected components. I don't need the number of connected components. I need the product of the 3 largest components. There should be a shit ton of 1s. Yes. Okay. Okay. The elves were right. They definitely don't have enough extension cables. You'll need to keep connecting junction boxes together until they're all in one large circuit. Continuing the above example, the first connection, which causes all the junction boxes to form a single circuit, is between the junction boxes at those two. Elves need to know how far those junction boxes are from the wall so they can pick the right extension cable. Multiplying the x coordinates of those two junction boxes. Continue. What do you get if you multiply together the x coordinates of the last two junction boxes you need to connect? Wait, the second part's easy. What? That's way easier than the first part. What the fuck? Too low. Oh. Hold on. Closest unconnected pairs of junction boxes until they're all in the same circuit. That's a little less easy. That's a little less easy. Okay, I was wrong. I misread the problem. Is this just building a min spanning tree on an implicit graph? Does that actually work? I need to take a look at Prim's algorithm and see if this makes sense that this would fit. I don't think what's being described here is the same as Prim's algorithm. But it might produce the same result as Prim's algorithm. The problem is that I don't care about the result of the algorithm, I care about which edge I'm adding last. So it might be, if I take Prim's algorithm, generate a min spanning tree, and then of those edges, whichever one's the longest is the one I care about. Because that would have been the one that, I think this algorithm and Prim's algorithm generate the same tree. I think this algorithm and Prim's algorithm generate the same tree. It's just how it's generating, it's a little different. Because this algorithm is not meaningfully distinct from the algorithm that we're talking about. Prim's algorithm starts with a single node and grows the tree from there. This is connecting shortest paths until the tree is fully connected. But I think the resulting tree is the same tree. I'm curious if this is going to generate the same tree. Intuitively, it feels like this should generate the same tree. I'm just gonna implement Prim's algorithm right out of the box right here. Yeah, but I don't... Oh, well... This must all have distinct weights, otherwise this couldn't have a distinct answer. I'm gonna try. I have never sat down to implement Prim's algorithm, which is kind of sad. So I'm gonna see what I can do. No, the weight on the edges is the length of them, the distance between the boxes, and we're on an implicit graph. So this is where it gets tricky. For every edge in... For box in unexplored, because we have a connection to all of them. In unexplored. Sorry, I've never actually implemented Prim's algorithm, and I'm trying to implement it on an implicit graph, so it's taking a little bit of brain power here. If neighbor in unexplored and weight is less than... If... weight is... AX, AY, AZ is current, and BX, BY, BZ is box. Weight is equal to, I'm not gonna write it again, this, and if weight is less than cheapest cost to that box, then cheapest cost to box is the weight, and cheapest edge to the box is I think I do want to store these as a list of edges like that. Then after this, result for each box in boxes. Why did I write each? For box in boxes, if cheapest edge to box is not none, then result append cheapest edge to box. Turn result. Yeah, buddy, me too. Edges is prim on boxes, and then edges sort first true. I mean, it doesn't really matter. I don't have to reverse it. Last is print Edges -1, 0. That's the cost of the most expensive edge. Too low. Square root. Gotta finally take the square root. Oh, no, it's not just the weight of it. Sorry. It's not just the weight of it. Okay. I was really hoping I wasn't going to have to debug Prim's algorithm. I was not prepared to debug Prim's algorithm, having only written it for the first time ever right now. I've used Prim's algorithm before to solve problems. I've used Kruskal's algorithm before to solve problems. I've never sat down to write Prim's algorithm on an implicit graph in Python, so... That makes sense. This makes sense, though. I understand how this algorithm works. I understand the basics of Prim's algorithm, but, like, seeing it in progress, like, seeing how it actually stacks up is interesting. I get it. That's cool. Most graph algorithms are just dynamic programming. I mean, at its core, it's kind of already dynamic programming. Your state space is like the unexplored portion of the graph and the explored portion of the graph. Oh yeah, are you said from the previous row, are you thinking of this problem? The tachyon beam one? I feel like I had an interesting approach to day 7. But mine was also a dynamic programming solution. I solved it recursively with memoization. Hi, Bubs up. Well, that's it for Advent of Code today. I'm going to switch over to Pikmin 2, so I'm going to bounce the YouTube stream.